So let's have a look at example number 5. Example number 5 of ORTools is named Partial Parent Grain Reconstruction to Clean TRWIP Steel EBSD Data. So what we're going to do is we're actually going to look at a new data set where we're going to have three phases. That's the parent phase austenite, then intermediate parent phase or first martensitic phase, the epsilon martensite, and then the second phase, which is then the child phase, like the final child phase, that's alpha prime martensite. In this kind of data set, there's a lot of different orientation relationships, and we're going to look at one of them or two of them and distinguish them. But I think we're just going to get started, and then you see what I'm up to. So again, as always, you can find example 5 on the main page of the ORTools toolbox right here. Let's jump into MATLAB. Again, if this is your first video, first example video, please start with example number 1, where I'm going to go a little bit more into the tiny details. I'm going to rush through a little bit through the first steps in this case. So this is example number 5. We initialize mtag, and then we're going to load a dataset. This time it's not a mtext dataset, but a dataset that we've provided with the toolbox, which is on TRWIP steel. So first we're going to calculate some grains with a kind of default threshold of 3 degrees. And when that is done, we can rename the phases and recolor the phases as in all the other examples. So we have iron FCC, that's actually our austenite, so we're going to call it gamma. Then we have iron BCC old, that is the alpha prime child phase. And then the last phase we have epsilon martensite, this is the intermediate kind of martensitic phase. We're going to just call this epsilon. And then we give them some nice colors. We go for green for gamma, red for alpha prime, and let's take this blue for epsilon. We're gonna set up the parent grain reconstructor, and we're gonna choose the parent phase gamma, and we're gonna choose the final child phase alpha prime. So now we can plot some maps, and we're gonna do this step by step so I can comment a little bit on them. So first we start with the phase map. So this is the phase map. So it looks a little bit chaotic if you've never seen a TRWIP steel before, but what you can imagine is that we have gamma phase in green. That's our basically austenitic high temperature phase, consisting of quite large polygonal grains as you know it. Then we have epsilon martensite formation, so that's the blue phase forming in kind of those bands as you can see. And then from those bands we can finally nucleate alpha prime. So we can see that all the alpha prime is actually situated on the epsilon as well. So this is a second order martensitic transformation. And yeah, the material has been cold rolled for 20 to 20% in order to get to this condition. Then the next map that we can plot are the inverse pole figure maps of the child and the parent phase. So this is the child phase, alpha prime. You can see that we form a lot of alpha prime along those kind of hexagonal grains actually. And then we can also look at the parent phase. You can see these are a little bit larger and they remind a little bit of like the normal polygonal high temperature austenite. One thing I would like to point your attention to, because it's going to be useful later to see, is that we have a blue phase right here and blue phase right here. So those actually fragments, you have the same orientation in gamma and in alpha prime. I'm going to come back to this later when it gets interesting. So we can now have a look at the grain boundary plots of the boundary misorientation. So we can see that actually all the grains have similar boundary misorientations between parent and child phase. So these are only the parent to child grain boundaries that are highlighted, apart from some of these spots right here that have a very, very low misorientation, which actually correspond to these blue parts. Then we can plot the same thing for the child to child boundaries, where we can look at the misorientation of these. And we can see that we have like, around 60 degrees misorientation, or almost 0 for some of the boundaries. So what are we gonna do next? We're gonna go into the define ORs, and now we have to actually say, okay, which orientation relationship do we want to work with? So what we do is we go into the peak fitter and see what kind of orientation relationships have been detected based on the parent to child grain boundary misorientation. And we can see we have this quite nice peak here, which is definitely the main orientation relationship. It has a little bit of a shoulder to the left as well. And then we have another orientation relationship with a little bit bizarre misorientation angle of 0. We are going to fit this now. So we're going to detect those two peaks, and again we use the maximum function value to determine the orientation relationship. So now that both orientation relationships have been determined, we're going to actually say all ORs, so we want to export both of these orientation relationships to work with them. Again, as in the previous example, if I just type in job, which is the return variable, we can see that we have two different orientation relationships here. And we get the first one by doing job 1 and the second one by job 2. So you can actually have a look at this first orientation relationship. We can see that the 1, 0, 0 is parallel to 1, 0, 0, 0 minus 1 is parallel to 0 minus 1. So this is basically a cube on cube orientation relationship, and a very accurate one, if I may say so. Whereas the second one is the more standard kind of Kodymov-Sachs orientation relationship. So if we now plot the grain boundary disorientation to those orientation relationships, so we see how well the grain boundaries fit to this. So we're gonna actually plot this in the inverse pole figure. Then let us see what we can find. So this is the first orientation relationship, so the one that was a little bit bizarre at 0 degrees, and we can see that we actually have some of the points here, the blue points, that have a low disorientation to the orientation relationship of cube on cube, but actually the axis, the misorientation axis, is scattered all over the place. So all the blue points are scattered, which makes sense, as in cube on cube, if there's no misorientation, the axis is basically defined to lie somewhere in that plane. Same, of course, for the child bases. And here we can see that there's actually no child-to-child boundaries that really fit this kind of misorientation or orientation relationship. Conversely, for the second one, you can see that we have a very good correspondence of this kind of main parent-to-child misorientation here, with quite a large margin, but it's bang in the center basically. And we can also see that all the child-to-child boundary misorientations can be associated with the misorientation axis and the angle of the orientation relationship. So the second orientation relationship is definitely the one we should trust in the larger scale. So what I actually want to do earlier, I'm going to do this now, is I'm going to plot the map of the disorientation as well. And what we can see here for this first orientation relationship, this weird cube on cube, you can see that there's some isolated corners where this actually fits very well. And for all the major parts of the map, this has a very high disorientation. And if we now, I mentioned this earlier, have a look at the orientation of the parent and the child face, we can see that actually these grains around here that had a very good agreement with this first orientation relationship, they have the same orientation as the parent face. So what these actually are, these are points that have been misindexed as alpha prime, where they actually are gamma. So it's basically an indexing error from the EBSD scan. So this is something we could detect with this kind of parent orientation analysis, and those ones are all marked, all the misoriented points. Just to double check, we already kind of expect what we're gonna see, but for the second orientation relationship, which is the actual orientation relationship, we can see that all the boundary misorientations are, most of them are below 5 degree, and those points here, they actually don't fit to the actual orientation relationship. So this points all at that these are misindexed points. So now that we know that these are misindexed points, we of course would like to get rid of them, right? And I know it's a little bit misuse of the parent grain reconstruction to use it as a cleaning procedure, but we can actually use it to reconstruct those points that agree very well with the first orientation relationship, but not so well with the second one. We can reconstruct those to the parent face according to this cube-on-cube orientation relationship, and this way we can actually clean the map. So let's just go through the steps. So the first thing is that we do calc grain boundary votes. This is the function where we are going to look at the child faces, and we're going to look at the neighboring parent orientation, so the neighboring gamma orientation, and see, hey, how well does this actually fit together um, with the specific orientation relationship. So we're basically going to calculate votes, and we're going to actually recalculate the parents from those votes. So if there's some grains where there's a potential parent that fits very well to the neighbor, we can actually take that parent and reconstruct it. I hope this was clear. So if we now look at the parent face, we can actually see that we have some new grains in here, and these are actually the reconstructed martensite grains that we've now just implemented into the parent face. And those small inclusions there, they were already there before we did the reconstruction. We can now do merge similar, and when we do merge similar, we get the same figure again, but now actually those inclusions have been eaten by the surrounding grains. So now we've effectively cleaned the map. So what we now want is to, these are still just grains, so we want to actually retrieve the EBSD data from that. And once we've done that, we can calculate the grains again on this new cleaned EBSD data set where all those, those misindexed grains have been filtered out, or actually not filtered out, but reverted to their actual face. So now we've done that, we can now just have a fast check. If we go again into parent face alpha, child face alpha prime, and we go into the peak fitter again. What we can see here now is that we still have the big peak from before, but what we don't have anymore is the 0-degree misorientation peak. So that one we've effectively removed and actually brought back to the parent face. So in this way we have actually used the parent grain reconstruction feature with this peak fitting functionality to clean a map. But in principle, you've seen that we actually used the parent grain reconstruction on a certain orientation relationship that some grains agreed very well with, while others didn't. And the same way, you could use this peak fitter to partially revert parts of your microstructure based on one orientation relationship, and then take the rest with another orientation relationship. So this is a good demonstration of this kind of case. I hope you liked the video, and bye for now.